Okay, hello everybody in the Friday class. You guys want to tell them hi? Hi. Awesome. Okay, so we're webcasting right into Monday, Wednesday, so that's cool. All right, we're doing a single mean example, and this is out of a sample of 40 coal cars. The mean coal tonnage per car was 74.5. Sample standard deviation 0.8. And we did this data before for a confidence interval, so now we're going to roll it into the hypothesis test. Okay, so that's a half a ton. Does this provide evidence that the company's claim of 75 tons of coal per car on average is dispensed into your coal car? Does it provide evidence that is too high? Test at 5%. Okay. So you can look up your confidence interval and compare it with this. So for us, our null hypothesis is mu equals 75, which is to say true average tons dispensed is 75. The alternative is mu. Since it uses the language too high, then I'm going to use a greater than. Okay, so it's a one-tailed test asked for. Mu greater than, greater than 75 is not going to be right, is it? I'm going to have to do less than. So wisdom required. We need to think about what's going on. Too high sounds like you use a greater than sign, but when I actually looked at it, it was the other way because of the way the numbers went. So you have to pay attention. There's no standard as far as the language goes, although of course with the math there is. The symbols. True average tons dispensed is less than 75. So they're putting out less than they claim. Okay, so here we go. The statistic. Again, I'm going to flip over to my table. And since I'm doing the mean, that's in the first one here. Mean is X bar statistic. Standard error sigma over rad n. Excellent. So we'll go and use that. Okay, so X bar, which was 74.5, standard error is exactly sigma over rad n. Now here's where an approximation comes in. So this is the squiggle symbol, whoever, I think Jenny asked me that, which is 0.8. That's my sample standard deviation divided by sample size, anyone? 40. Yeah, so the standard error is 40. I've got those. Oh, I think that one is about 0.13. Okay, so I got a standard error. That's good. Let's set up the curve, and I need to be getting you guys out of here, so let's do this guy here. Null distribution, 75 is the claim, right in the middle. We wind up with 74.5. So I'll stick that over here on the left. I have the mean distribution, z-score distribution. So the z-score for 75, that's what I'm after. So z is stat, I better write this out, stat minus parameter over standard error, which is 74.5 minus 75 over 0.13 And z-score turns out to be minus 3.95. Okay, so minus 3.95 is my z-score for that. So the p-value then is the probability that z is, we're going to use the same sign as the alternative hypothesis, just like we said before. In this case, it's less than minus 3.95. And when you flip to your table, you're going to read it and see that it goes off the bottom of the table. Therefore, it says use the following approximation, 0.0001 for values less than negative 3.49. So that's my number. So right here, p-value is 0.0001. So my decision, p-value 0.0001 is less than 0.05, which implies reject H null. Okay. We conclude the true coal dispensed is less than 75 tons on average. Their claim is wrong. And now we've, quote unquote, proven it using a hypothesis test. Okay? Understanding what that means. Hello, class. I recorded the example here, single coal car, on a different file, so that's why this is showing. But we're going to continue. We're doing chapter 23, and my design is for the TA to work a couple examples with you, the single mean example, antacids, and difference of means, as you will request. So what I'm planning on doing right now is we're going to go into the exercises. I'm going to do number 2, okay? You have number 1 in the R script solutions, and you also have number 3. So I'm doing 2 and 4, and we'll do them by hand and on R. That's the design. Okay, so, and God bless you, my wife and I and my kids are enjoying a prayer conference in Santa Maria, so look forward to seeing you actually quite a ways off. So, praise the Lord. Okay, but have a happy Easter. Okay, so we're going to do this one. Welcome to the new movie pre-show. Before you can see the newly released movie you have just paid to see, you must sit through a variety of trivia slides, snack bar ads, paid product advertising, and movie trailers. Although the total barrage of advertising may last up to 20 minutes or more, a particular theater chain claims that the average length of any one advertisement is no more than 3 minutes. When I was at Frozen, they showed this very lengthy Disney thing. It was way more than 3 minutes. It wasn't an ad, though, I guess. To test this claim, 20 theater ads were randomly selected, found to have an average duration of 3.5 minutes, standard deviation 1.3. Those are both sample. Do the data provide sufficient evidence to indicate that the average duration of theater ads is more than that claimed by the theater? More than, note that. Okay, test at the 5% level of significance, and we'll do it by hand and on R. Okay, so I've put in an extra space here. So let's go ahead and run this baby. We're going to do our 4 steps. So this is number 2. Null hypothesis is mu equals 3 minutes with alternative mu greater than 3. That greater than comes from the language more than, which was given in the question. So we watch for that. Equals 3 says that the true average ad is 3 minutes. And of course, we understand that's or less, right? Okay, so what we're really testing is, nah, that thing is too long. So true average add is over 3 minutes. Okay, so there's our null and alternative hypotheses. I'm going to note that alpha is going to be 0.05. Okay, so for number 2, we are looking for our statistic, which in this case is the sample mean. Please check page 112 to confirm we are using means and what we have here. In this case, we got an average of, what was it, 3.5415. Okay, so that's my stat. My standard error then is formula rad, or sigma over rad n, which we are approximating with a 1.3445 divided by the square root of 20. And so for that I get 0.3006. Great. So we're going to sketch the bell curve, and it sketches out like this. 0. Sorry, it's not a decimal. It's exactly 3 minutes. That's the null distribution. Now the data says 3.5 minutes. So, wow, we're coming in high. 3.5. So I'm going to put that up here. 3.54. That's on the level of the mean. If I convert to z-scores, then the center is at 0, and I need to find my 3.54. So the z-score for that is always statistic minus parameter divided by the standard error, which is 3.5415 minus 3 over 0.3006, and that works out to be 1.80. Pretty friendly numbers. So the p-value then is step 3, and that 1.8 goes right here, 1.8. The p-value is the probability that I get this extreme of a result or worse. Or worse means shade into that part of the tail. And so the p-value, by definition, you can look this up on page 113. We always put probability that z-score is some relationship to my observed value. So what sign do I use? I use the same exact sign as I find in my alternative hypothesis. So z greater than. Over here I'm using a greater than, so I'm only shading one side. Thus, probability z greater than 1.8, I'm going to bip over to the table in the back of my book, and I want 3.30, wait a minute, yeah, I want 1.8, excuse me, 1.80, which is a 0.9641. So 0.9641, I'll take that, and if I observe, is that my shaded region? No, since I want greater than, I have to do 1 minus 0.9641, which is 0.0359. So p-value 0.0359. It's a one-tailed test, that's my result. If it was a two-tail, this would change by doubling. not equals, and I would double that number. It's not. So p-value is 0.03, which is less than 0.05. Using our pre-established decision criteria, we now reject the null hypothesis. Using that rejection, we can come up and draw the alternative hypothesis as the conclusion, which says the true average add is 3 minutes, and so the alternative is the true average add is over 3 minutes. Okay, so that implies we conclude that the true average add is indeed over 3 minutes. Okay, now that we've done it by hand, let's show how to do this on R. Since we're doing the numeric data, I've got it here, chapter 23 movie ad. I'm just going to click on it in R Studio, and it doesn't give a name, it just calls it V1. There's the 20 observations. So I'm going to go ahead and hit my up arrow so I can access that and attach. Now V1 is the name, so it's direct, it's easy, V1. The command is t.test. So if I just do t.test on V1, by default, it's going to run. Now, we want to pay a little attention here. We've got the mean, so that looks good. And it says alternative hypothesis, true mean not equal to 0. That is not what I want, and the p-value is incorrect. So there are two things that I need to do. The first one is the argument is called mu, and you set that equal to your hypothesized value, which in our case was 3 minutes. So here's mu. Now, the p-value got a lot nicer, and true mean is not equal to 3. So p-value is looking better, but it's doing a two-tailed test. So let me do that argument, and that is alternative, alternative. In our case, you can do greater, less, or 2 dot-sided. If you put nothing, 2 dot-sided is the default. We're doing greater than. So popping it in, alternative hypothesis greater than 3. The t, this is what I got for z. I haven't addressed this in class yet, so I'll do it now. What we've used is a z-score. In fact, this standard deviation was estimated to be 1.34. It's unknown. If we had the exact value, z would be the correct statistic to use. If it's random, then the sample standard deviation is used, and there's a distribution called the student's t distribution. It's a technical detail that Utts doesn't detail, though she mentions it. And so the t statistic has the same interpretation as the z-score, namely number of standard errors away from the mean. It's a wannabe normal curve, so it has a little bit thicker area out on the tails, a little bit thinner in the middle. But other than that, the concepts all are the same. So going back to my R, I'm going to get a little higher probability because of a little thicker tail. So we computed 0.03. The R is going to get 0.04. So there's a 1% increase in that. And that's a technical detail that Utts and I are not considering important enough to focus on in this class. Your colleagues or your fellow students in biostats, they do the details there. Okay,